My name is Janice, and I am on the SANCOLD YPF committee. And we are very thankful for having Jacques here, who will be presenting the Ingula PSS-Some presentation for us, where he will be presenting on some design and construction challenges for the Ingula pump storage scheme. Jacques is a professional water engineer specializing in dams and hydropower works. He is a professionally registered engineer and is also a technical executive at GIB. Just some rules with regards to the webinar. Please, can we all leave all questions until the end? If you think you might forget your question, you're more than welcome to leave it in the chat and we will get to it at the end of the webinar. So thank you, Jacques, again, and thank you everyone for attending.
Thank you, Janice. Thank you for the introduction, and good afternoon, everyone, and thank you for the opportunity. I'll start the presentation just by showing you a video, an overview video, a drone video of the project, just to bring you into the picture. And then after the video, we'll start the presentation. Okay, good afternoon again, everyone. As Janice has mentioned, The webinar is on the Ingula pump storage scheme, and because of the size of the project, it's impossible to discuss everything. But what I will discuss is some of the design and construction challenges we had. And so why are we talking about a project that's been done 6 years ago? And I think it was such an amazing project that you can't talk about it too often. And there's also a number of lessons we've learned on the project that I would like to share, some of them at least with you this afternoon. And then also recently, pump storage schemes with all the renewables going in, it's starts making a lot more sense to build more pump storage schemes because the sun is not shining during the night. So you can use solar, for example, to pump water to an upper reservoir, and then during the night you can generate electricity using a pump storage scheme. So just this layer of the presentation. Start with a short introduction, the project layout, some statistics on the project, and then we'll get into the meat of the presentation, the design and construction challenges, and I've grouped them together, firstly for the upper dam, Bedford Dam, then the lower dam, Bramhoek Dam, then the tunnels, both the headrace and the tailrace, and then the powerhouse itself, and then there's time for questions at the end. So just, I think immediately from the start, there's Bramhoek Dam, the lower reservoir, and just there at the top you can see Bedford Dam sticking out. There's the escarpment, very close to the boundary between the Free State and KZN. And from the top side, there's Bedford Dam. The power intake sits over here. The channel from the dam to the power intake, the surge shafts, and then there in the distance you can see Bramhoek Dam at the bottom, and there's the edge of the escarpment. I would like to immediately point out two things. The first one is the small size catchment area of the upper reservoir, because that I'll discuss that in a little bit more detail. And then the second thing is this beautiful wetland downstream of Bedford Dam, and how that impacted on the design. And because of this, environmental considerations were taken very, very seriously on this project. So what's pump storage? For those of you that's maybe not familiar with pump storage, it's when water is stored in an upper reservoir, and then when you have peak demand periods, you release the water from the upper dam through a turbine, generate electricity, pump it into the grid, and then when there's too much capacity in the grid, you use the same reversible pump turbine then to pump the water back into the upper reservoir. So it's basically almost a battery that you charge during off-peak times and that you use during peak times. Now in South Africa, we've got 3 bigger pump storage schemes. The one is Palmmead, close to Gordons Bay in the Western Cape. That's 250 megawatts. Then we've got the Drakensberg pump storage scheme. That's 1,000 megawatts. And then Ingula, that's 1,332 megawatt. So where is Ingula? When you drive on the N3 down to Durban, you go through Harrismith, you go down the Van Reenen's Pass, past the Biltong store, just approximately there. Just before you...
Okay, any sound?
Just before you turn right, if you go straight, you go to Ladysmith, you turn left at Bestas, and there's the Ingula pump storage scheme. Just to zoom in a little bit. As you've seen as well, just get my laser again. There's Bramhoek Dam, Bedford Dam, the provincial boundary, and the tunnel alignment between the upper and the lower reservoir, straight over here to the outlet works inside Bramhoek Dam. If you look at a section through the project, immediately I want you to please recognize that each of these rows represents 100 meters. So approximately 500-meter head, 1 kilometer low-pressure head raise tunnel, then another approximately 1 kilometer inclined high-pressure shaft, a 2.4 kilometer tail raise, very big tail raise tunnel because there's only one tail raise tunnel, 9.4 meter internal diameter with a concrete lining varying from 600 millimeter to 1.2 meter. So there's 2 head raise tunnels, 2 surge shafts, surge riser, surge shaft, in total 200 meters high. 2 of them inclined high pressure shafts, also 2 of them, and then 1 tail raise tunnel. Now it all looks very much straightforward and pretty simple from here, but just to zoom in here to show you how it actually looks underground, this is what it looks like. So even for us that worked on site for quite a number of years, so we often got lost underground in these tunnels. So very massive machine hall excavation in mud rock, 184 meters wide, 45 meters high, 25 meters wide, and then 2 80-meter high surge chambers, shock absorbers, together with the surge shafts. And then you see all the tunnel work. So we've got the inclined high pressure shafts coming here, bifurcating. And then we've got the 4 turbine units, the bus bar tunnels into transformer hall. And so very intricate, complicated layout underground. And that's all 350 meters underground. So let's look at some of the statistics on the project. And it's interesting that in 2017, it used to be the 19th largest pump storage scheme in the world. And today it's the 25th largest pump storage scheme in the world, of which the largest, if I'm not mistaken, is in China, 3,600 megawatts, massive pump storage scheme. Compare that to Ingula's 1,300. And then I know that Australia, they're also busy, I think, with 2 or so pump storage schemes. I think, if I'm not mistaken, of which one of them will be the largest pump storage scheme in the world. As I've mentioned, very big excavation in mud rock for the machine hall, 184 meters long. In total, about 3 million cubic meter of material were excavated, both for the surface works and the underground works. And this is a staggering statistic, 15,000 tons of steel lining for the waterways. And those were rock tough steel, so about double as strong as your normal 450 MPa yield strength steel. Because if the steel wasn't strong enough, then the steel cans would just have been too heavy to handle. So that's why the steel is extra strong, and it was imported from Germany. The welding consumables, 450 tons. Total length of the welds, 24 kilometers. I've mentioned the 350 meter underground. That's 116 stories, just to put it into perspective. Operating range varying between 460 and 480 meters. The generating flow rate is 350 cubic meters per second, and the pump rate is 241 cubic meters per second. Now, it's interesting to note a pump storage scheme is actually a net energy user. So you use more energy than what you generate, and the overall efficiency is around approximately between 70 and 80%. I think Ingula sits at 77%. So you can store enough energy to generate approximately 16 hours. All those tunnels you've seen, if you add them up, it's about 10 kilometers. And I've indicated to you the 9.4 meter, 2.4 kilometer long tail raise tunnel. On the job, the contractor achieved near world record concrete pump lift. I'll tell you more about this later on. 3,000 jobs were created, and this main inlet valve you see here, of which we had 4, weighs 150 tons. So just some of the project statistics. Right, now let's get to the individual parts of the project. Let's start by the upper dam. So it's a concrete faced rockfill dam. So the entire dam is constructed from rocks in various sizes. There you can see the plinth line. intake tower, plinth again running up the left bank. And the reason for this plinth is to tie the concrete face, concrete membrane that you put on top of the rockfall. You tie that to the foundation at this plinth structure. There's a little bit further during construction. You'll see that's the concrete face part of the dam. The first starter slabs for the face going in. And this side is a clay core rockfall dam. There you can see the clay core. And the reason for that, simple, there's two main reasons. It's just cheaper to construct a clay core here, but we didn't have enough clay to do the entire dam from with a clay core. And also for the concrete face, you can't just pinch that concrete face into nothingness here. So at some stage you have to stop it. So it just made sense then to have a clay core rockfall dam on this side. What's interesting, if you carefully look at this photograph, you won't see a spillway. And that's just linking it back to my first comment on the small catchment. Because of the small catchment, 17 square kilometers, you can actually absorb the floods between the full supply level of the dam and the non-overspill crest level of the dam. So, but it's a pump storage scheme, so it's not that simple, because the actual pump rate, that 241 cubic meters per second, if you route that through the reservoir, you can actually get the dam to spill, but that's only possible if there's a flood entering Bramhoek Dam at the bottom. So very, very low probability of the dam spilling, but for that reason, we only have a spill section here, an 80-meter long sill, and that's why we don't have a spillway chute with a dissipating structure like you would normally see on a dam. There's the face slab going in. So from the mixer truck, they would discharge the concrete down a chute onto a conveyor belt. You spread the concrete, place it, compact it. There's a working platform. And then behind it, there's another working platform for the guys to immediately do concrete repairs if necessary. So that's a very efficient way of forming the concrete face. And you do it in panels, because if you don't do it in panels, just because of the sheer size and the movement, it will crack. Remember, it's only a concrete membrane to seal the dam. There's the water stops between the joints of the face slab. There you see the copper water stop, and there you see a central rubber water stop. The modern trend nowadays is to go for a top shutter, not top shutter, top water stop. So because you often get honeycombing between the central or below the central rubber water stop. And there's the finished product. Now, looking at one of the design challenges we had and focusing on the bottom outlet works here, because of that beautiful wetland downstream of the dam, firstly, the environmentalists told us they want us to be able to flood the wetland once in every 10 years. So using that, we've back calculated to determine, but what flow rate do we need in order to flood the wetland downstream? So, that worked out to 50 cubic meters per second. So now we were actually stuck between a rock and a hard place, because you release 50 cubic meters per second here, but now you don't want to erode the wetland going downstream. So what we did, and I think if I remember correctly, the late Erlen Snell told us to go to Suikerbossie. So from the Vaal Dam, there's approximately 20-kilometer pipeline to Suikerbossie, where they're also dissipating a lot of energy before the water flows into the main canal feeding Gauteng. So the initial layout of this bottom outlet works was based on Suikerbossie, and that's the initial layout. So to try to keep it simple, we had one radial gate, stilling basin, a wave suppressor, and then the stilling pond, the water flowing back into the wetland. But then for those of you that's hydraulic engineers, you would know the Fruit number. It's a flow velocity divided by the square root of G times D, where D is the flow height coming out of here. And we couldn't get the fluid number high enough in the stilling basin to get an effective hydraulic jump. So basically all you can control to get the fluid number higher is this D, because the velocity basically depends on the height of the dam. So, but it also doesn't help to make that D smaller and smaller, and you end up with, let's say, a 1 meter high radial gate, 10 meters wide. Just gets not impractical. So that's why we've ended up with 2 dual radial gates, outlet gates. So that sorted out the stilling basin and the energy dissipation in the basin. And then the stilling pond was optimized by doing a CFD analysis. And from the first runs, we saw that this area we had basically a dead zone over here. So all we did was to change the excavation to follow that flow line over there. So just saving a bit on excavation there. The second issue was we got flow recirculating, so the water would flow out and actually flow back into the stilling pond. So flow recirculating over here, and then the effective flow length just became this approximately from here, that length of sill. So we set ourselves the criteria, we wanted the flow velocity back into the wetland to be less than 1 meter per second. So to change that, this wall was opened up, as you can see here. So there's the original geometry and then the optimized geometry, and that wall was curved as well, just to make sure you get positive outflow without that flow circulation. So there's the optimized layout, and there's the final constructed stilling basin, stilling pond. Just the contractor decided this in this wetland we've got peat soil, 7 meter thick peat soil. So the contractor decided to take it out, stockpile it, and at the end, as part of the rehabilitation, it was put back. And if you go there now, these reeds have grown back all the way up to the downstream toe of the dam. Actually, the impact on the wetland from that sense was really minimal. I've mentioned the peat soil, the 7 meter thick peat soil in the river section. Now you can see, as you can see on this photograph, not easy to excavate that. So how do you do it? How do you eat an elephant? Piece by piece. So that's also what the contractor did. He formed these compartments and he dried it out as much as possible, and then he excavated it. Just while we're looking at this photograph, for interest's sake, this entire outlet works were positioned on the left side of the wetlands. So that basically when the contractor was on site, he immediately had access to construct this. So because we wanted him to finish this, divert the river through the bottom outlet works, and then you can construct the rockfill across it. There you can see the temporary river diversion, and this was just a little bit of a filter to filter the water before it was released, filtered through this material back into the wetland. It's always important, try to make it as easy as possible for the contractor. And in this instance, we also tried to minimize the footprint or the impact on the wetland. The contractor came up with this clever idea because of that peat soil sloshing out of the trucks when they're driving uphill. He had these earthful plugs at the back of the trucks to prevent that from happening, just for interest's sake. Then a little bit further during construction, this was close to the end of construction, if not already the end. So you can see, I think in 2010, we had about 0.5 meter of snow. So for this the cold weather, it definitely had an impact on the face slab concrete mix design. So for that reason, air wasn't drained into the concrete mix. But what I actually want to talk about on this slide is the erection of this bridge. 40-meter long steel bridge was manufactured in 4 sections. So there, 3 of the sections were already bolted together. There's the 4th section. And what happened was the original method statement from the contractor indicated that he wants to lift 2 of the pieces or sections from the crest and 2 from the bottom. And then when the rigging was done for this top crane, the outrigger on the downstream side was very close to the downstream edge of the crest, and that's where the material is not compacted that well. So for that reason, in the end, it was decided to lift only 1 piece from the top and 3 sections from the bottom. But then this crane was originally erected only to lift 2 sections. The total weight of this bridge was 50 tons. So then the contractor, because of this change, had an option, 2 options. Either you dismantle the crane, you move it closer to the dam, and then erect it again, or bringing an additional 10 tons of counterweight, which in the end was what he did. And just to show you how Murphy sometimes work, this crane is very, very expensive because there are not too many of these cranes in the country. So the day the crane arrived on site, it started snowing. And I think we had to wait something like 2 or 3 days before the contractor could erect the crane. So that's just the way sometimes things work out. So the bridge was erected on a Saturday when there was very, very little construction activities ongoing. But very tense few hours. And eventually, what you don't see on this photo is the third crane. So these 2 cranes would bring the sections together. The third crane with a man cage with the people inside would then bolt the sections together in midair. So quite, as I mentioned, quite a bit of a tense exercise until it was finished. Then we can't talk about Bedford Dam without mentioning the fossils. So the contractor started with the excavations for the dam foundations. We started finding these tree fossils, and then it just ballooned. We just found fossils everywhere. In the end, there were more than 60 fossils were discovered, tree and animal fossils. And Eskom, the client, they appointed a paleontologist that was permanently on site. So it actually worked very well. After every blast was declared safe by the safety officer, the first guy on site would be the paleontologist, and he would say, please take that piece of rock, put it aside for me, and then he investigated it further. So there you can see 2 of the animal fossils, one in this direction, actually 2 on top of each other. There's the other one. See the ribs. There's the tusk of a Dysonodont. Apparently, these Dysonodonts were as plentiful as sheep in that area 60 million years ago. There's a tooth of a crocodile, Gorgonopsid, 3-meter long crocodile. And inside the crocodile's stomach, they found a Lystrosaurus. So there's the Gorgonopsid, Dysonodonts, and the Lystrosaurus. Apparently, in those days, it was essential to have long teeth or tusks to survive. So a wealth of knowledge that was actually discovered. All those fossils went to universities. They investigated it further, and some of it came back to the visitor center on site. But a very interesting, unexpected part of the project. Another environmental consideration was the bald ibis birds. There you can see the nests and the droppings on this beautiful waterfall that was inundated by the dam. There's a cave here where the Boers in the Anglo-Boer War were staying, and apparently it's so big that they had 100 sheep here in this cave. We still used to see lots and lots of inscriptions on the rock. Also, what the farmers told us was under this rock there was a lot of inscriptions that this rock fell off, and that was all unfortunately lost. There you can see why it's called a bald ibis. We actually worked very well together with BirdLife SA on this project. So initially, they wanted us to replace those bird nests that were inundated. And then we suggested, because of the deep excavation due to the geology on the right flank, why don't we use that upper part of the dam and recreate new nests for the birds in that sort of tucked away part of the dam. And they thought it can work, and they actually produced these sketches for us. Said, okay, just create these shelves for the birds. We think it'll work fine. And then there's the original position. Then during construction, we started talking more and more with BirdLife South Africa. And then we came to the conclusion that everywhere you see these birds, they're nesting above water. So then we all agreed it's not going to work to have the nests there. And fortunately, at the time, the contractor needed a bit more rockfall to finish the dam. So we agreed with the contractor. This was a lot closer to the main dam than the quarry. We asked the contractor to prepare these pockets in the side there for the birds to make their new nests. So I think in the end, a win-win for everyone. But guess what happened? Keep in mind that shotcrete was only from above the full supply level to the top. And this is what happened. They made the nest just below those pockets we've made. But at least the pigeons love the pockets. Then let's go to the lower dam, Bramhoek Dam. It's an RCC dam, so completely different to the upper dam. So for those of you that's not familiar with RCC, it's a concrete, roller compacted concrete that you bring in, but you treat it like earthfill. So you would bring it in with a dump truck, dump it, spread it with a dozer in 250 millimeter layers approximately, and then you compact it with a roller. And because you're doing it in long sections up to a meter height, you induce joints in the RCC, otherwise it will crack everywhere. And there where you induce the joint, you don't see the joints here yet. You install a water stop on the upstream side. So you actually tell it where to crack, and then you just seal that crack. So completely different to the rockfall dam at the top. There's the dam nearing completion. And there's the final dam with a crump measuring weir downstream of the dam. So let's see a few of the interesting things that happened at Bramhoek. Now, just imagine yourself seeing the core lock for a core that was drilled into this material. I think you can agree that once you get there, you would think you're on pretty solid rock, and you only have to excavate up to that level. But what we've discovered on site was these huge boulders, just actually rock blocks, loose rock blocks, standing on top of each other with clay seams in between. And those clay seams also made the grouting difficult because you couldn't get the grout to go in there. So struggled to get to seal all the joints. Here you can see some more of those loose boulders that in the end had to be removed. So for the right flank, the excavation levels were a bit deeper than the original design for that reason. So whenever you're in dolerite again, working with dolerite, watch out for this. You don't end up in the same situation. Okay, please have a careful look at this photograph, and carefully look at what nature shows you. You can see this material originally was over here, and that material was over there, and this material slipped from there. So no wonder then when the contractor started excavation for the dam foundation against the lower left flank, the material just started slipping and slipping. And when we got to this stage, we thought, no, everything's fine. Look at this tree, and it slipped again. So this resulted, understandably, in a claim to the contractor, which he won in the end. What I also want to point out to you, please have a look at that little survey beacon over there. Because what happened was, can't remember what the surveyor surveyed one day, but he stormed into our offices and said, no, the dam's moving by a couple of centimeters or so. And in the end, we discovered because of this, it's not the dam that moved, but actually the survey beacon. Okay, that's the lower dam. Now going to the tunnels, the head race tunnels, and in particular, low pressure head race tunnel. So that first kilometer over there, 1 1/8 slope. Important to keep that in mind. So the contractor decided to do a split shutter for that section of the low pressure tunnel. So he would have a shutter on the invert of the tunnel, place the concrete up to there, and then bringing the top shutter for the top stage of the concrete. So he started a full-scale trial, and he just couldn't get rid of these blowholes. Now, to cut a long story short, he just basically tried everything from different placement methods, different shutter oils, different varying vibration efforts, mixed designs, imported sand, gap grading in the aggregates, imported aggregates, I think all the way, imported dolomites from Pretoria, lower slump, higher slump, ordinary plasticizer. He just tried everything in the mix, and he couldn't solve the problem of getting the blowholes, because what happens is you vibrate the concrete, the air comes out, and it gets stuck between the shutter, and it just sits there against the shutter, resulting in these blowholes. And obviously, for friction losses in the tunnel, you don't want these blowholes. So what was specified is a controlled permeability formwork liner, but it's expensive. And it takes time every time to fix to the shutter, because you can use it once, maybe twice, and then you have to replace it. So you can understand why the contractor tried his best not to place the CPF liner. So what is just a bit more on what is a CPF liner? So there's the shutter. You fix it to the shutter, and then you place and you vibrate your concrete against it. So the air can escape through the liner and the water drains out. And the result of that is you also reduce the water cement ratio against the shutter. In the first 1 or 2 centimeters against the shutter, you draw your water cement ratio right down to as low as 0.4. So you end up with a very strong, very durable concrete against the shutter and against the flow. So it makes a lot of sense for tunnels. Our flow velocities in these tunnels, in the concrete tunnels, went up to as high as 5 meters per second. So you can understand why this CPF liner was specified. So I think a very important lesson we've learned there. So there's just to show you how it looks. It's not without its problems as well, because I think for the first 1 or 2 pours, it just detached from the shutter. It actually folded into the concrete, and then it's a big mess to chip it out and to repair the concrete again. But once the guys got it right, it worked like a charm. Now, the concrete tunnels, the water at Ingula is very soft. So because of the soft water, you get soft water attack. And for a long time, it was debated whether is it necessary or is it not necessary to paint the tunnels just to delay this the soft water attack and the degrading on the concrete of the liner of the tunnels. So in the laboratory on site, these specimens were cast and they were painted with epoxy paint. And then some of those samples were fully coated. Then the water was circulated continuously over these specimens. And then every week or so, a lab manager would go there with a brush and he would brush it lightly, just sort of to mimic the abrasion inside the tunnels. And there you could see the effect after 65 days, after 130 days. So based on this, the rate of mass loss of the concrete was determined, and that average, because you could weigh these samples, and based on that, the average rate of surface loss was estimated to be 1.1 millimeter per year. So 11 millimeters in 10 years. So, and based on these results, it was decided to paint the tunnels. So a very interesting exercise that was done on site. Then the tail race tunnel, and this is not, there's not any lessons learned. It was just something interesting. So for the final tail race tunnel inspection, the contractor used a bucky. So that for that 2.4 kilometer section, we walked behind the bucky, to make sure there's nothing left behind in the tunnels, because you don't want a piece of aggregate or a piece of steel to go through your turbine once you commission the system. So then we got to the end, everything was done already. So the bucky was picked up and lifted out, gone out of the tunnel. So just something interesting that happened. So all that was left was we were 2 or 3 guys now waiting for the contractor to lift us out with the man cage and the crane sitting outside. And mysteriously at that moment, the crane broke down and it started raining. It was the middle of the night and there was this cold draft going through the tunnels. It was so cold. And so we were stuck there for a few hours, and till today, we think it's just the contractor getting one back on the engineer inside the tunnels. Just before the bucky was lifted out, the oil was obviously drained out. Okay, looking at the inclined high pressure shafts coming down at that bifurcator upstream of the turbines. We had this steel bifurcator plate and a crotch plate in the middle. So you've got the shell welded to that crotch plate. To show you a photograph, there's that 150 millimeter plate in the middle. And then the shell, 46 millimeter thick steel of that rock tough steel welded to the plate in the middle. So everything was done. The weld tests were done. Everything looked fine. The contractor did his sandblasting, and everything was ready to paint. And our inspectors picked up this crack in the weld. That's a 65 millimeter fillet weld. And then to just take one step backwards, the specifications originally included post-weld heat treatment. But post-weld heat treatment is not easy to get right. And if you mess it up, you actually change the material properties. So the contractor requested the supervisor and the client whether he can leave out the post-weld heat treatment. And it was agreed that let's see how it goes without the post-weld heat treatment. And unfortunately, it cracked. So then the experts came in, and after the expert reviews, it was decided that post-weld heat treatment is in fact required. Now, just to explain to you what it is, and it's almost like baking a cake. So you preheat the steel to 180 degrees, then you weld at 250 degrees. This is the normal can welding and heat treatment. And then there was a controlled cooling down period for 10 hours to 90 degrees, just to make sure that all the entrapped hydrogen was removed from the weld. And then you allow it to cool down by itself, and then you do your non-destructive testing. Now, with post-weld heat treatment, in addition to this, that weld was heated up again to 300 degrees at a certain rate of 40 degrees per hour. Then it was soaked for 4 hours at 550 degrees. You can see it was some massive exercise. And then there was a controlled cooling down again, and then it was allowed to cool down naturally, and then you do your final non-destructive testing. So major exercise, but in the end, it was required. Now, for a moment, put yourself into the contractor's shoes here. So now the tunnels were constructed, the rock support was installed. Now you need to install the steel cans from where the pressure inside the tunnels required the tunnel to be steel lined. So if you're the contractor, how would you do it? I think it makes obvious sense to install the steel cans through the surge riser, shaft and riser onto a trolley, and you bring it down the inclined high pressure shaft, you encase it in concrete. So the contractor proposed to bring in the cans from the top and to pump the concrete from the bottom by installing 2 pipelines adjacent to the cans. So you just keep on extending the pipeline as you go. Because keep in mind, you bring in the cans, then you concrete encase. So every time take out the concrete team, bring in the grouting team, take out the grouting team, bring in the guys to paint the tunnel. You see, from a program point of view, it just made sense to do this. But we were, as the supervisors, we were very skeptical whether this would work, because look at this. Your static head is 400 meters. The density of concrete is 2.5 times that of water. So there you've got a water equivalent of a kilometer head. But now you need to overcome the friction losses as well. So for a typical water pipeline, where friction loss is, say, 1 meter every 100 meters, for pumping concrete, that friction loss is 1 meter per meter. So there was another, when you get to the top, another kilometer of head. So in total, the pressure required at the pump was equivalent of 2 kilometers of water. So there's the steel can going in, steel can in position, just before the concrete encasement around it. There's the hopper for discharging the concrete, and the pump to pump the concrete up. And there's the contractor designed self-compacting mix. So not requiring any vibration, because you can see the access was a bit difficult. And just to come up for a supervisor a little bit closely, before we got to the top, we had blockage and we lost the one pipeline. But fortunately, the contractor installed two pipes, one on the other side as well. So just interesting stat. I think I've mentioned all of this. I'll come back to that one. It took 36 minutes for the concrete from being discharged in the hopper before it's discharged at the point, and 12 cubic meters just to fill the pipeline, getting close to the top. So we investigated this a little bit just to see whether it was a world record in terms of how far concrete was pumped. And we saw at one of those Dubai towers, they pumped concrete 606 meters high, but it was a vertical lift. And we've pumped it, or the contractor pumped it, more than 1 kilometer. So not the highest, but still very, very long pump line. Okay, quickly going back to the lower reservoir again. And I think on the Ingula, interfacing was probably the most difficult between all the contracts to get the interfacing right. So the underground works were constructed by one contractor and the dams by another contractor. So it was 2 separate contracts. So the dam schedule allowed for impoundment on the 17th of April 2010. You see, so the last thing you want in a pump storage scheme, because it's constructed to where you've got the 2 dam sites close to each other and a very high head difference between the 2 dams to generate the most electricity. So what you need to do on a pump storage scheme is just fill one of the reservoirs once, and then every year you only have to top up the losses. So you can actually get away by constructing this in a very small river. But still, importantly, at Ingula, our hydrology study indicated that the dam could fill, because of the varying rainfall we've got in the country, anything between 4 months and 3 years. So the underground works contractor started falling behind program, and now we're starting to go into the rainy season at the dam. So eventually the dam was impounded on the 4th of November 2010. And then again, Murphy, in November, we got just above average rainfall. December, double the average. And in January, triple the average. So the dam filled up in about 5 months. So the contractor realized that he's in trouble, and he constructed a berm around the outlet works just to buy him a little bit more time to finish the works. And he just made it in time, but unfortunately he couldn't remove the berm in time, and it overtopped. So we insisted that he remove the berm underwater by dredging. So he claimed, and in the end it went to arbitration, and in the end the contractor lost this claim. So just to show you, there's the dam filling up. There you can see the berm. And here's the pontoon he brought in from Durban with the stabilizing arms. So you'd pull it into where you want to dredge, lower the stabilizing arms, fix it in position. And before that, the excavator with the long arm was attached to it, and then the contractor excavated that berm underwater. Just an interesting aspect on the rock support for mainly the machine hall. So you can imagine you've got this 184-meter long, 45-meter wide excavation underground. So it's a massive excavation, and this rock, 350 meters of rock above your excavation, was sitting there for millions of years, and now you remove the support. So you can understand why you need a lot of rock support. And keep in mind, we're in mud rock here that degrades rapidly when it gets into contact with oxygen. So the designer specified what we called a 3-phase rock support system. Just to show you, there's the side of the tunnels, there's shotcrete and mesh going in, different layers, you can see the thickness there. And there's the final underground excavation works just before the concrete work started. So you can see massive underground excavation. Now, I'll tell you a little bit more on the 3-phase rock support system just now, but just for interest's sake, this mesh was replaced by, firstly, the contractor tried steel fibers in the shotcrete, and then in the end, he used synthetic fibers because it just worked a lot easier than to fix the mesh, and the steel fibers also blocked the shotcrete pipes. So in the end, we settled on the plastic fibers. So there's the crown of the machine hall, 50-meter long, so rock support, staggered. And without going into all the details here, we've got the primary rock support, secondary rock support, primary rock support consisting of rock bolts and cable bolts, and then the secondary rock support consisting of cable anchors. So what's the difference between a rock bolt, cable bolt, and a cable anchor? So cable bolt is almost like a roll bolt you buy in a hardware store, except that's a cable, that part of it. So you've got a mechanical coupler, and then that part's a cable, and then you grout it in afterwards once it's tensioned. Rock bolt, very similar, also a mechanical coupler, but that's a bolt instead of a cable. And then an anchor bolt looks like this. So for the mud rock, and this is where the 3rd phase came in, for the mud rock, you would fix that part. It would the rock would release, and we actually would stretch this cable anchor a little bit until it was instrumented, until that movement stopped. And then it was grouted up via this pipe that you see here. That part of the anchor was grouted. So that's the 3-phase rock support. But it will obviously not be the same on every pump storage scheme, but in mud rock, that is what was required. Now, we don't have too many more slides to go. So the spiral case around the turbines were put in position. Remember, there were 4 of these, and a very interesting part of the design. What we wanted is between the spiral case steel and the concrete, you want a small gap. Because what you want is when this is pressurized, you want the steel of the spiral case to first take up the first initial load, and then only does it get supported by the concrete around it, by the reinforced concrete around it. So what was done on site was to pressurize this to 22 bars. prior to concrete encasing it. And then after concrete encasement, the contractor monitored the temperature of the water inside the spiral case, as well as the concrete temperature. And when that fluctuation was less than 0.2 bar in 24 hours, and basically the water temperature inside the spiral case, when that stabilized, the pressure was released, ensuring that little small gap between the spiral case. So just a very interesting part of the design that was followed out on site. Then there's the machine hall. You can imagine there was some huge concrete pours here. That was, for example, there's the draft tube being encased, massive concrete pours. And the specification allowed the contractor to place up to 2.5 meter heights the concrete. There you can see around the units also fairly large concrete pours. And on this draft tube concrete encasement, we got temperature cracks in the concrete. So the rule of thumb is when the concrete on the surface, the concrete temperature, say it takes on the ambient temperature, say 20 degrees, and the concrete in the middle is more than 20 degrees warmer than the concrete on the surface. So more than the hydration temperature, more than 40 degrees, there's potential for the concrete cracking. So what we did was we relaxed the specification that specified 25 MPa at 28 days. We relaxed that to 25 MPa at 56 days. And that allowed the contractor to increase his fly ash content to 50%. The temperature was also monitored continuously while the concrete hydrated. And also the contractor, and remember this is underground, so you don't have the sun heating up. It's still that temperature went up as high. And the contractor also added ice to his concrete, and he really lowered the temperature. Some of those pours, the temperature went down to as low as 11 degrees. So really a lot of effort that was put in by the contractor, but in the end, it solved the temperature crack problem. So there's just to show the finished project, there's the operating floor. So you've got the turbine floor, generating floor, operating floor in the machine hall. There's the turbine floor. There's the epoxy coating on the operating floor. And there's the final finish in the main powerhouse. So thank you very much. I hope you found it interesting. Please, if there's any questions.
Thank you very much, Jacques. That was really a very interesting presentation. I'm busy taking down notes on things that I need to watch out for when I do construction and go on to designs and go on to site for construction. There is a question in the chat by Alan Shamali. Alan, would you like to ask Jacques the question yourself, or can I read it out? Okay, I think I'll read it. Alan wrote, thanks very much, Jacques. So at the Q&A, with respect to the left bank of Bromhoek, please expand on the details of the retaining wall between the CFRD and the left bank, abutment clay core rockfall dam, i.e. concrete retaining wall, clay core, including chimney, drain, interface, etc.
And maybe, Janice, I should just share my presentation again.
Yeah.
Okay, so we're going back to the Bedford. So I assume it's this retaining wall he's talking of.
He mentioned left bank of Bromhoek. Yeah.
But then he mentioned the clay core. Just read the second part of the question.
Okay. So it's please. So with respect to the left bank of Bromhoek, please expand on the details of the retaining wall between the Oh, no, sorry. And Alan mentioned it is Bedford Dam that he's speaking about. He just
Okay.
said, yeah.
Yeah. Okay, thanks, Alan, for the question. You see this this concrete face, if we can just look at the next. So the concrete face panel, you can see it becomes shorter. And at one point, it can't pinch into nothingness. So so for that reason, we stopped the concrete face rockfall dam at this point. So you need a separation between your concrete face, and you also need something to place your clay core cut off on this side against. So we have a sloped, I think it was a 8-in-1 slope, concrete slope there, and then downstream, like you've asked, downstream of this clay core, we had a chimney filter and a blanket drain as well. Yes, I hope that answers the question.
Hi, are there any other questions? You can raise your hand or unmute yourselves. There is another message in the chat from Sandeep. He says, thank you very much, Jacques. Very interesting and informative presentation. Kind regards, Sandeep Shinde, and from the UK.
Thank you, Sandeep. It's a pleasure.
Are there any other questions? You're welcome to unmute yourself. I do not think we have any questions.
I'm getting off the hook. I'm getting off the hook lightly.
No, I think we're all just so awed by what you've just shown us. It's amazing to be able to see all the construction photos and everything. So I'm still trying to process everything in myself, and I'm sure everyone is doing the same. But oh, okay, there's one question. We have one question. Hi, Odon.
Hi, this is Odon from Zutari. I was just curious. You mentioned the water stops and the trend to go to water stops on the face. What water stops did you end up using at? Was it Bedford Dam as the upper one?
Yes. So we had a copper water stop, a 1mm copper plate with a central rip at the back, and in the center we had a 250mm rubber water stop. But
Okay,
we experienced a few problems on site with getting honeycombing underneath the rubber water stop. They had a central bulb with two sides, and then in a few places, and the problem is you get honeycombing, but it stretches over 5 meters, and it's very difficult to grout it up and to do those repairs. But the other consideration, I mean, it also depends where you are, because you have to look at, is there a possibility that it could be vandalized or not? Because it's easy when it's on the surface, it can easily be vandalized. So that's sometimes why you put it inside the concrete. But it makes the shuttering a bit more complicated, because your side shutter for those panels have to allow for the water stop to go through.
No,
So
the
it's very
rubber water
easier.
stop is quite heavy.
Yeah. Yes.
As you mentioned, you have the issue with the compaction behind it. And then I've got another question. I was just curious about the size of the recurrence interval of the diversion flood for the Bedford Dam. You said there wasn't really much of a catchment, but there was the wetland. So I guess you might have issues of quite high backwater. I don't know. I'm just kind of thinking off the bat there.
No, not really. I think that 1 in 10-year flood, if I remember correctly, was 60 cubic meters per second. But during construction, we didn't get close to that. So actually, we were in a sense lucky during construction. It was the highest flow rate we had. I think we went up to probably 1 cubic meters per second.
Well, thank you.
Just to mention, Odin, on that the face slab panels, the other reason is your reinforcement gets a lot more simpler if you don't have a central water stop. Because it's a lot easier to reinforce and to put in the shear to make sure you don't get the shear failure on the concrete face on the edge there. So that's also another something to keep in mind on those joints.
Oh, thanks. Good tips.
Okay.
Thank you. And I think Nico has a question. Nico Opperman, if you can unmute yourself, please.
Yes, Jacques. Hello. Thank you for the nice, interesting presentation. I'm just interested with regards to the planned construction period and the actual construction period that the contractor actually finished in.
Okay. On the dams, the planned construction period was 3 years, just over 3 years, and they finished it on time and within budget. On the underground works, it was a different story. The original construction period was planned at 4 years, 4 or 5 years, and it ended up being, I think, close to 9 years. So it's there was a very big overrun on program for the main underground works contract.
Okay, and then just another question on the steel bridge that you showed us. Is the floor, was it like a bonded concrete type of floor, or was it a steel grating?
Steel, it was just a steel plate.
Okay, steel plate. Okay.
Yes, and interesting, I didn't mention, you can't mention everything if you have limited time, but what I didn't mention was, and the contractor actually came up with a very clever idea to get that bridge, because you put it down, and before you grout you put it down on the bearings and then you grout it in. But to get the level perfect, he actually made a sand box with holes on the sides. So he would put the bridge down on the sand box, and then with a water jet, he washed out the sand under the bridge and slowly lowered until it was the elevation was perfect, and then he grouted it in. So I thought it was a very practical and very clever way of doing it to get the bridge vertical alignment perfect.
Well, thanks, Jacques. That's interesting. Who was the two main contractors on the dam and the underground works?
Okay, actually, I expected the question. I've got a slide. Let me just show you again, right at the end. Apologies for running through the entire presentation again. There we go. So you can see the number of contractors, so also can understand the interfacing issues. So the aggregate was up front because the rock was coming from the Bramhoek Basin. So that was an advanced contract done by B&E, Access Roads by Grunica LTA, Concord and Wilson Bailey Homes, joint venture constructed the 2 dams. Those visitor center and admin building you saw on the video, those were done by Trencon. Then the main underground works was done by a joint venture between CMC and Improgilo. And then the lot A, B, C, D, E, as you see there, lot A and D were done by Voith. Coney Cranes did the cranes, and Siemens the transformers, and the auxiliary electrical plant was done by ABB.
Okay, thanks, Jacques.
Okay.
Thank you, Nico. Jacques, there is a thank you from Jeremiah. He says, thank you very much for a good presentation. I'm learning a lot from Zambia. He's from Livingston, Victoria Falls Power Station, ZESCO. There is another question from Godfrey. Is ice concrete the best strategy to reduce concrete heat of hydration instead of admixtures?
Look, concrete technology improved tremendously over the last number of years. And I'm not a concrete expert per se, So I'm actually not sure whether you've got, I've got no experience with chemicals to cool down the temperature, but just the traditional way was the contractor just adds ice to the mix. But I don't know. I'm not sure whether it could be possible. I won't be surprised because there was, as I mentioned, there was a rapid improvement on all these super plasticizers and admixtures, and there's amazing things you can do with it these days.
Thank you. And then Kogi also saying, thank you, Jacques. That was a brilliant presentation. I'm wondering what the wetland specialist was thinking when they suggested 50 cubic meters per second. Did they want to flush it away completely?
No. They wanted just to flood it, just to basically drown it. So we calculated the 50 cubic meters per second. So we did a back calculation in order to determine the flow rate. So so they didn't tell us the 50, but yeah. So basically, what the viewpoint was, you want the wetland not to realize that we've constructed a dam upstream. So being able to mimic floods and then just the normal releases from time to time. So yeah, we actually calculated the 50 cubic meters per second. What it sort of started happening in South Africa, as far as I'm aware, around the 2000 Berg River Dam was, well, I think was the first dam with this really massive bottom outlet to release floods or to mimic natural floods. I mean, and if you look at the old dams, they got away with much smaller outlet works, and it's a big cost component for the project. I think that bottom outlet was probably 30% of the total cost of the dam at Bedford. So it's a huge cost component, but that's the extent of that clients are willing to go to accommodate the environment.
That's awesome to hear that we, as engineers always need to worry about these things, and we do care for our environment as well. Another question from Barkrat Ali. He says, hi Jacques, thanks for the presentation. Can you please tell us about the curtain grouting for both dams, the depth of grouting and the methods of grouting?
Okay, it was a cement brace grouting. Both were done vertically. To intersect, you try and intersect the joints as best as possible. The upper dam was actually very easy to grout because it was sedimentary rock and it was competent rock with very specific open joints between. We had mud rock, sandstone, the way it was deposited. If there was a big flood, it picked up the heavier particles and it deposited sandstone. If there was a smaller flood, it picked up the smaller particles, deposited the mud rock. So we had this clearly defined open joints at Bedford that was actually very easy to grout. So we did and the grouting depth on both dams was approximately 2/3 of the maximum depth, was approximately 2/3 of the height of the dam. So in Bedford it was around 30 meters, a little bit less at Braamhoek. And we started, I think the spacing of the primary holes was something like 12 meters apart. And then secondaries, obviously 6, quaternary 3, tertiary, quaternary, and et cetera, et cetera. And I think the closest spacing we came at Bedford was in one area, we went down to 0.5 meter spacing, if I remember correctly. And at Braamhoek Dam, it went down to as much as 1/4 meter but not everywhere, only in certain areas. So you would assess the grout take based on the primary holes, then decide the secondary, et cetera, et cetera. So grout pressure, you have to be careful not to hydrofracture the rock, especially when at Bedford where you've got a nice open joint so you can very quickly get that hydrojacking force and you actually lift the rock. So something to consider, you must be very careful. You try to find that optimum between not getting hydrojacking and but you want the grout to penetrate as many of the cracks as possible. So, but that just comes from trial and error on site. Obviously, the maximum pressure you should specify, but then the actual best working method you sort out on site. I hope that that answered the question.
Yeah, I think, thank you. And continuing with the messages in the chat, from Hayati from Malaysia says, good presentation, thanks a lot. Peter Pike also says, thanks, Jacques, excellent presentation. Alan Shamali mentioned Berg River Dam was 200 meters cube per second to mimic first natural floods, exact inflow hydrograph. Yeah, and then I have a question with regards to tunnel lining. Would self-compacting concrete be better than CVC?
It's just you see, if you use conventional concrete, it could have worked, and especially where you've got a vertical shaft, it's a lot easier to just use conventional concrete. But in this instance, the better application was just because of the access, and it's not easy to work there. And I'm a firm believer, if it's not easy for the contractor, and especially for his workmen on site, you're going to struggle to find a good product. So in that instance, I think it was the right thing to do.
Okay.
But it's not to say CVC couldn't have worked.
Okay, no, thank you. Does anyone else have any questions? We still have 9 more minutes. Bokrat says, thank you, Jacques, for your answer. Can you please tell us about the pressure used in the curtain grouting?
Yes, you're taking me back a long time now. I think it was, we grouted at a maximum pressure at depth, because it also depends on the deeper you go, the higher the pressure. But remember, then you get the actual gravity helping you as you go down. So you only measure the pressure at the collar of the hole. So you have to take that into account. I think we went to pressure at the collar of the hole down to only or up to 2-3 bar, not much more than that. But I can't remember exactly. But it will be in that region.
No, thank you very much. Do we have any other questions from everyone? We still have 7 more minutes. Okay, there's another question from Edwin Lilly. Could any of the accidents that occurred on the site have been prevented?
At Bedford, we had no fatal accidents. On Bramhoek, I also don't think we had any fatalities. On the main underground works, we had, I think, close to 10, of which 6 was one incident. And yes, Ed, it's I think it could have been prevented. But it was a difficult. I think what sort of, I don't want to say it resulted in the accident, but when you've got it was because it was an underground works contract, it fell under the Mines Health and Safety Act. And because it's a Mines Health and Safety Act, the client remains responsible. So here you have a contractor constructing the works, but he's actually not responsible because the client's responsible. The client remains responsible. He can't delegate his authority to the contractor like you can do when you're working under the Health and Safety Act, the Occupational Health and Safety Act. So I think that was the first problem. And then, I mean, we went through method statements, then safe work procedures based on the method statement. And then every morning the contractor had his toolbox talk before they started doing the work. And that accident in the inclined high pressure shaft where 6 people was killed was just negligence. That trolleys that were hoisted up and down the tunnel to do the grouting work inside the tunnel was had 4 anchors to anchor it to the steel liner with these bolts that you screw into the steel liner. And what happened was the contractor's guys only screwed in one. The other one, they just gave 1 or 2 turns, and they didn't They didn't screw in the bottom ones at all. So then there was something caused a shock load on the trolley, and the one bolt pulled out of the liner, the other one ripped off, and that trolley ran down the shaft, hit the second trolley, and two trolleys ran down to the bottom, and they collided with that crotch plate that I saw on that I showed you on the photographs. So definitely it could have been prevented. And it was a human error. It was just negligence. The guys didn't. They got slack because they're doing it every day, and it's so yes, I suppose all accidents can be prevented, but it is just one of those really, really terrible things that happen on site that I don't want to go through ever again.
No, thank you. Thank you, Jacques. Is there anyone else with any other questions? I think that's a wrap. No other questions. Thank you again, Jacques, for taking out the time. Yeah.
But Janice, we can't finish on such a negative note. There
Oh
must be
no.
another question.
Everyone wants me to share the recording because they say that there's so much to learn from it. But even yeah, okay, I've got another message from Philip and Lobby. Said thoroughly enjoyed this presentation. Thank you, Jacques. And yes, even though it is a negative note, I think it's very valuable for us to learn from it. And it's also important for us to take notes from what you have shared with us, so that us as the younger engineers that do go into design, we take into account what you have learned and what you have experienced to make sure that we actually go forth and do our work properly and to standards and ensure that nothing like such happens. And Alan Shamali has asked, when is your PhD due?
Thank you, Alan. But just one last word on the inclined on the safety. What we've experienced on site, it's so easy to do a raise boring. So you would drill a hole, how many meters down? You get to the bottom, you fix a cutter head, you pull it up again, and then you create a hole approximately 2 meters. This is how the contractor did the search shafts. And it's so much simpler and safer than trying to excavate and construct those inclined shafts. So from a safety point as well, I know it's a longer flow path and it more friction losses, and it's you actually can generate less electricity as a result. But actually on site, it's a lot easier to construct a vertical shaft than to have an inclined shaft. So maybe just please consider that if ever you're busy designing a pump storage schema.
Thank you. No, that we will definitely note down. Thank you again, Jacques. There is thanks from Michael as well. And Alan Shamali says, thanks very much for an A1 plus 100% plus 5-star presentation. Yes, definitely. Thank you very much, Jacques, for taking your time out to give us this presentation. We really do appreciate it. Thank you. We know you're very busy, but yeah, very thankful that you're doing this presentation for us.
Thank you, Janice, and thanks to you as well for organizing it.
No, thank you. No, and then there's a lot of thank yous. So there's thank you from Lucy. There's thanks for a great presentation, Jacques. There's a question from Fulu. How massive would those surge tanks and what pressures can they withstand? So I think it's the last question we have.
Fulu, yes, the surge riser was steel lined for this, so the bottom 100 meters in total, the riser and the surge shaft in total 200 meters. The bottom 100 meters was steel lined, so they could take at least the maximum pressure at the bottom was, because the shaft is 200 meters, the maximum pressure there would be 200 meters. Because what happens if you get a shock wave or the let's say the wicket gate slamming shut around the turbines, you get that shock wave running up and down. The water just oscillates inside the surge shaft until eventually it stops. So the maximum pressure there was 200 meters, and then in the surge riser and the surge shaft itself, the concrete part, it was 20-meter diameter, 20 or 21-meter diameter, and so the maximum pressure at the bottom couldn't be more than 100 meters, because otherwise the water would have jet out at the top. So, but that will give you an idea. So the concrete part was a maximum pressure 100, and then for the surge risers at the bottom 200 meters. Obviously, at the upstream of the turbines, there the pressure would go more than 500 meters, because the operating head was between 460 and 480. So with the dynamic pressure, it could easily go more than 500.
Thank you very much. Yeah, so thank you again, Jacques. Now time is running up. There is also a thank you from Thea. Thank you so much. Great presentation. Enjoyed it a lot. And yes, I'd like to thank everyone for attending our SANCOLD webinar as well. Thank you, Jacques, for hosting it, for presenting. We will have another presentation next month regards to an introduction on geosynthetics. We will send that email out soon and hope we'll see everyone there. Thank you very much again, and hope to see you all soon. And if you'd like to present a presentation like what Jacques has done for us, please send me an email and we'll organize the time slot for you. Thank you, and bye-bye.
Thank you, Janice. Thank you, everyone.
Thank you.
Bye-bye.
Bye-bye.